In this video, we're going to talk about rates of change and shapes of curves. Let's start by talking about the average rate of change. Suppose that f is a function, and y equals f at x. That means x is our independent variable and y is our dependent variable. Or in other words, x is the input and y is the output. And the value of y is determined by our function f. The average rate of change in f over an interval from a to b is given by the formula that you see here. The average rate of change is equal to f at b minus f at a divided by b minus a. So the top is the difference of the outputs, and the bottom is the difference in the inputs. So we can say that in words, and we've written it down here, so that the average rate of change is the change in the outputs divided by the change in the inputs. So the average rate of change is measuring the ratio of the change in output to the change in input. Or in other words, it's measuring how much the function values are changing compared to how much the input changes. Let's compute an example. Find the average rate of change in the function f at x equals x squared over the interval 2 to 4. So in this example, a is equal to 2 and b is equal to 4. So the average rate of change is equal to the difference of the outputs, f of b minus f at a, divided by the difference of the inputs, b minus a. So in this case, that's f at 4 minus f at 2 divided by 4 minus 2. At this point, we need to compute f at 4 and f at 2, but we can do that using this formula. This function squares the input, so this first input is 4, so f at 4 is going to be 4 squared. And the second one, the input is 2, so the output is going to be 2 squared. So that means that our average rate of change is 4 squared minus 2 squared divided by 4 minus 2, which is 16 minus 4 divided by, well, 4 minus 2 is 2. 16 minus 4 is 12, divided by 2 is 6. So the average rate of change is 6 for this example. Let's talk a little bit about notation. We denote the average rate of change in the function f from a to b using this expression here. Now that letter that you see, this letter is called delta. That's the Greek letter delta, but it's the capital delta. So this is delta f over delta x. Let's just write that down. Delta f over delta x. So we denote the average rate of change in the function f as delta f over delta x. And that's the difference in f over the difference in x. In mathematics, it's very common to use this letter delta to mean change in. So the delta x is the change in the x values, and delta f is change in the f values. So that's f at b minus f at a. And this gives us a way of writing the average rate of change without actually writing out the words every time. Average rate of change in the function f. So let's do another example. Find the average rate of change in this function over the interval 5 to c. So what is this function? This function f at x is x squared plus 2x minus 8. And we're looking at the average rate of change over an interval from 5 to c. Now notice that there's a c here. C looks like a letter, but this letter stands for some number. We don't really know what that number is, but we're just going to assume that it's bigger than 5 so that this notation makes sense. If c was smaller than 5, then this wouldn't make sense. So in order to have an interval here, c has to be some number bigger than 5, but we don't specify the actual value. So let's compute the average rate of change using our new notation. So the average rate of change in f is delta f over delta x. So this is the difference in the f values, the outputs, divided by the difference in the x values, the inputs. So the two inputs are 5 and c. So on the bottom, we're going to have the larger one minus the smaller one. So on the top, it's the output at these two inputs. So I put the larger number x first. It doesn't really matter if you do the larger one first or the smaller one first, as long as you're consistent. So here I have c minus 5, so in the numerator I have f at c minus f at 5. The two outputs need to correspond to the two inputs, so whichever input goes first, the corresponding output has to also go first. So you're measuring the change over the interval from 5 to c. So this is the difference in the x values that are the inputs, and these are the differences in the corresponding outputs. Okay, so let's actually compute these. Well, we need to use this formula. So let's compute f at c. So f at c is equal to what? Well, here the input x is the letter c. So that means we just replace every place where we see an x. So this is f at x, but x is equal to c. So every place that you see an x, you just replace it with c. So this becomes c, this becomes c, and that becomes c. So it's going to be c squared plus 2 times c minus 8. So that's f at c. F at 5 is equal to, and now we just replace every x with 5. So it's going to be 5 squared plus 2 times 5 minus 8. The first one, there's not a lot you can do to that because we don't know what c is, but we can simplify this last one. So this is 25 minus 2 times 5 is 10, or that's plus actually. 25 plus 10 minus 8. So 10 minus 8 is 2. So 25 plus 2 is 27. So that means our average rate of change, delta f over delta x, is going to be c squared plus 2c minus 8. So that's f at c, minus f at 5 is 27. And we're going to divide this by c minus 5. So we can simplify this a little bit because we have this 27 minus, or it's a negative 8 minus 27. So this is c squared plus 2c minus 8 minus 27. And this is divided by c minus 5. So this is going to be c squared plus 2c, and then that's going to be minus 35 over c minus 5. Now, as it happens, we can factor the numerator. So how are we going to do that? Well, in order to get this c squared, there has to be a c here and there has to be a c here. Now, the thing that we need is we need to get that 35. It's a negative 35, so that means one of these has to be positive and one of them has to be negative. This is a 2 here, so that means the difference between these two factors that give us 35 has to be 2. So how do you get 35? Well, one way is 7 times 5. And now notice, well, you can check to make sure that this is right. C times c is c squared, then 7c minus 5c is 2c, and then positive 7 times a negative 5 is a negative 35. So the c minus 5's cancel, and now we're just left with c plus 7. You should always simplify your answer as much as possible. So let's do another example. Find the average rate of change in this function over the interval from 3 to x. Well, notice here, x is suddenly our number, our upper bound. It's from 3 to x, where x is some number bigger than 3. X is no longer our input variable. In this case, our input variable is t. Okay, so let's go ahead and compute this. So we want to compute the average rate in change, the average rate of change in f, where the input variable is t. So that's delta f over delta t. So it's the difference in the f values. So f evaluated at the larger t value minus f evaluated at the smaller t value divided by x minus 3. Okay, and now we want to compute these f at x and f at 3. So again, all we have to do is just wherever there's whatever this input is, you just take this t and replace it with that input. So our first input is x, so you just replace the input t with x. So f at x is x squared minus 12. We're just replacing t with x. So this is f at t, and this is f at x. So wherever you see a t, you just replace it with x. So that's x squared minus 12. Now to compute f of 3, or f evaluated at 3, you do the same thing. So now, wherever there was a t, you replace it with 3. So the only t was right there. So it's 3 squared minus 12, which is 9 minus 12, which is a negative 3. So now let's compute the average rate of change. So it's the first one, f at x, which is x squared minus 12, minus the second one, which is negative 3, divided by x minus 3. So this one is equal to what? So x squared minus 12 minus a minus. Minus a minus. If you have minus a minus, that's a plus. So this becomes plus 3. Minus a minus is plus over x minus 3. So x squared minus 9, negative 12 plus 3 is negative 9, divided by x minus 3. Now this numerator is the difference of squares, so this one's actually pretty easy to factor. So this one is x minus 3 times x plus 3. And notice in the denominator we also have an x minus 3. So that means we can simplify this. The x minus 3's cancel. And we're just left with x plus 3. And that's our rate of change from 3 to x. Let's do another example. Find the average rate of change in this function over the interval from 2 to 2 plus h, where h is some positive number. Here our function f is a function of s, so our independent variable is s. F at s equals 3s squared. Now this interval goes from 2 to 2 plus h, where h is some positive number. Really, that's just a way of saying that the number that we were calling b. So if this was b, that really just means that b is greater than 2. Because b is equal to 2 plus h, and h is some positive number, so 2 plus h must be bigger than 2. It's just another way of saying some number bigger than 2. So let's go ahead and compute this average rate of change. In this case, it's delta f over delta s, because our input variable is s. So it's f at the larger of the two, 2 plus h, minus f at the smaller, divided by the larger one, minus the smaller one. Okay, so let's compute these things. So we know what f at s is. Now we want to compute f at 2 plus h. So we do this in the way that we did before. Wherever there's an input, we replace s with that input. So in this case, s is 2 plus h. So we're going to replace s with 2 plus h any place that an s appears. So here's s. We're just replacing that with 2 plus h. So the only s is right here. So we're just going to replace that s with 2 plus h. So this is going to be 3 times 2 plus h quantity squared. So that's 3 times 2 squared is 4 plus 2 times h is 4h plus h squared. So if we want, we could just multiply that out. So 12 plus 12h plus 3h squared. So that's f at 2 plus h. The next one we want to compute is f at 2. So any place that there's an s, we just replace it with a 2. So that just becomes 3 times 2 quantity squared. Well, that's 3 times 4, which is 12. So delta f over delta s is equal to f at 2 plus h, which is all that stuff right there. 12 plus 12h plus 3h squared minus f at 2. Well, f at 2 is 12, so that's just going to be 12. And all of this is divided by the denominator is 2 plus h minus 2. 2 plus h minus 2. The nice thing about writing our larger number as 2 plus h is that this h is the difference between the two. So we're starting at 2 and we're going to 2 plus h. That means we're increasing from 2 to 2 plus h, so the difference between them is h. So h is that difference between them, and you can see that right here. The difference between the s values is 2 plus h minus 2, and so of course these 2's are going to cancel. That's not the only thing that cancels. In the numerator we have a 12 here, and then we're going to subtract this 12. So those are going to cancel as well. So we end up with 12, that's supposed to be a 2. We end up with 12h plus 3h squared divided by h. So notice that we have an h in the denominator, and we also have some h's in the numerator. So we can factor out an h from the numerator, and we'll have h times 12 plus 3h divided by h. So we factored an h out of the numerator. So we factored out one h there, so that's why there's a 12 here. 12h, h times 12. And this was 3h squared, so if you factor out one h, there's still going to be another h there. So h times 3h is 3h squared. This is distribution. This is the distributive property. H times 12 plus 3h, you multiply the h by each one of these. 12h plus 3h times h. 3h times h is 3h squared. But now we see that there's a factor of h in the numerator and a factor of h in the denominator, so these will cancel. And you're just left with 12 plus 3h, like so. Let's talk a little bit about notation. So if y is equal to f at x, then we think of the inputs as being different x values. And so we might want to look at the average rate of change from one x value to another x value. So since these are both x values that are unspecified, we call the first x value x1, or x sub 1, and the second x value we call x sub 2. So we use these subscripts to indicate that both of these numbers are input values, x1 and x2. These are both x values, so these are two inputs. In this case, we would write the average rate of change as delta f over delta x, but that would just be, again, the difference of the f values over the difference between the x values. But now we can just see that these are x values here. So in the denominator we have two x values, and in the numerator we have f at x2 minus f at x1. For each input x, there is an output y. So we can write y1 as the output for x1, and we can write y2 as the output for x2. So in this case, the average rate of change, well, it's the difference in the f values, the difference in the output values, divided by the difference in the input values. But the output value for x2 is y2, and the output value for x1 is y1. So what you see here is that you have y2 minus y1 in the numerator, and in the denominator you have x2 minus x1. So that's the change in y over the change in x. So the average rate of change is the change in y divided by the change in x. This is a nice way of thinking about it because it calls to mind something else. The difference in the y's over the difference of the x's, that's the slope of a line. And in fact, the average rate of change in f over an interval from x1 to x2 is the slope of the line from the point x1, y1 to the point x2, y2. So if this is my first input, so here's my graph, here's my first input x1, and here's my first output y1. So that gives me a point. And my second input x2 corresponds to the output y2, and that gives me this point. So if I draw a line connecting those 2 points, then the slope of this line is going to be the difference in the y values over the difference in the x values. That's our delta y over delta x. And what is that? That's the slope of the line. It's also the average rate of change in f over the interval from x1 to x2. So we can see that this average rate of change is actually the slope of a line passing through 2 points of the graph of the function. Let's introduce some terminology. A function is said to be increasing on an open interval if the values of f at x increase in size as x moves from left to right. So here's an example. This is actually the graph of y equals x cubed. So as x goes from left to right, that means x is getting larger. X gets larger as it goes from left to right. And y is also getting larger as we go from left to right because y is increasing in size. So on the left side, over here, you can see that the output value is negative, and the output value y just gets larger and larger and larger as x gets larger and larger. So as x moves from left to right, x is getting larger. So what we're seeing in this graph is that as x gets larger, so too does y get larger. And when that happens, we call the function increasing. Notice that we're saying that it's happening on an open interval. So remember what an open interval is. An open interval is something that doesn't include the endpoints. So an open interval is something of the form a comma b, where we don't include the endpoints. So this is the set in set builder notation. It's x such that a is strictly less than x, strictly less than b. So we don't include the endpoints. So we can talk about a function being increasing on an interval of this kind, an open interval. So if there's such a thing as an increasing function, it's easy to believe there's a decreasing function. So a function is decreasing on an open interval if the values of the function decrease in size as x moves from left to right. So here, this is the graph of y equals 1 over x, at least for x positive. And as you can see, as x is going from left to right, that means x is increasing. The y values are actually getting smaller. So as x goes from left to right, so this is our x value, and this is our y value, then on the graph, we're moving downwards. We're moving downwards on the graph as x goes from left to right. So as x is increasing, y is getting smaller. So that means that our function is a decreasing function. This leads us to an important notion, which is called a local maximum. A local maximum is a point where a function changes from increasing to decreasing. So here's a graph of some function. It kind of looks like a parabola, but who knows what it's doing outside of this image. It might turn around and go up on either side. It might not. We don't really know. This is just a portion of the graph. On this portion of the graph, you can see that the function is increasing at first, and then it's decreasing. So up until this point. So here's some x value. I don't know what it is. Let's call it c. C. So on this interval, f is increasing. And on this right interval, f is decreasing. What that means is that the function is increasing for a time, and then it decides to decrease for whatever reason. So that gives us sort of this mountain shape or this hill shape, and that means that there's a peak, and that peak is what we call a local maximum. That's because if you look close by, if you imagine that you're standing right on this mountain, right on that peak, if you look either way, the graph falls down in either direction. That means it doesn't get any bigger nearby. That's what we mean when we say it's a local maximum. That means it's the largest possible y value on some open interval. So we're just looking close by. So a local maximum is just when you have a largest possible value in some small region. So we're just looking at nearby. So if there's a local maximum, there's also something called a local minimum. And a local minimum is a valley. A local maximum is the peak of a hill, and the local minimum is the base of a valley. So if you're standing at the base of this valley, then in either direction, the hillsides are sloping up before you in either direction. So this is the smallest y value close by. Now, it might not be the smallest y value all over, because this graph, who knows what it's doing outside this region. It might come up here and then turn around and drop away. We don't know. We don't know if it does that. So we're only seeing a small portion of the graph. So we don't know if this local minimum is the smallest possible value, but it is nearby. And that's why we call it a local minimum. This is a point where the function changes from decreasing to increasing, and you can see that here. So let's call that x value c. And you can see that here, f is decreasing. And over here on the right, f is increasing. So our function goes from decreasing to increasing. So if it does that, it must leave some valley. And the base point of that valley is your local minimum. Collectively, local maximums and local minimums are called local extrema. Extrema is the plural. If you only have one, it's called an extremum. These come from the Latin. So extremum is the singular and extrema is the plural. And like I said, this comes from the Latin. Now, a function can have many local extrema, or it might have none at all. So on the left, you see a lot of peaks and valleys. Every single one of these peaks is a local maximum. Every one of these peaks is a local maximum. And as you can see, there are a lot of them. So these are all local maxima. Again, maxima, that's the plural. So I don't know that I want to draw arrows to all of these because there are so many. But all of them are local maxima. And let's change the color, and all of these are local minima. And you can see there are a lot of them. That's okay. There can be as many as the function wants. The function does what it wants. These are all local minima. So you can see that there are a lot of maxima and local minima. On the graph on the right, this is some translation of y equals x squared, but it's just moved to the right and moved up. This one, you can see there are no local maxima here. There are no local minima here. There are no local extreme values here. Okay, let's look at some examples. For each of the following graphs, which will appear on later slides, let's determine where the function is increasing and where it is decreasing, and let's give the coordinates of the points that are local extrema, based on what we see in the graph. So here's our first example. Okay, so you can see that it's increasing until it reaches -3, and then it changes to decreasing. So it's increasing on this interval from negative infinity to -3. Notice this arrowhead here. That indicates to us that this keeps going down forever. This arrowhead here indicates that it's increasing forever. Now I say that this is decreasing, this is going down, but the function is increasing here because remember, when you talk about a function increasing, it's as x goes from left to right. So as x goes from left to right, the function is increasing. So we're starting over here somewhere and we're moving to the right. And as we're doing that on the graph, it's getting larger and larger. So y is getting larger as x gets larger. So it's increasing here. It's also increasing here. So that means it's increasing on this interval. So increasing on the intervals from -infinity to -3, and let's say the union, let's put in the union symbol here, 1 to 3. So it's increasing on those intervals. And of course it's decreasing on the one in the middle. -3 to 1. Notice that we're leaving off the endpoints here. At this point here is a local maximum. This point here is a local minimum. At that point, it's not increasing or decreasing. It's increasing to the left of it, and then it's decreasing to the right. So it's not increasing or decreasing at that point. So that's why we don't include -3. Don't include -3 in any of these, or 1 for that matter. At 1, you can see to the left of 1, it's decreasing. To the right of 1, it's increasing. But at 1, it's not doing any of those things. So now we can just write down that the local maximum is this one right here, and that the coordinates of that point are -3 and 4. So the local maximum is at the point -3, 4. And that's what it asks us for. Let me just scroll back. For each of the following graphs, determine where the function is increasing and where it's decreasing, and give the coordinates of the points that give you local extrema. So the extreme value of the function, the local extreme value is actually 4 because that's the output value. It's happening at -3, that's the location. But the point, it asks for the coordinates of the point, and that's -3, 4. So that's our local maximum. Our local minimum is right here. So local minimum, what are the coordinates of that point? Well, the x-coordinate is 1 and the y-coordinate is -2. So the local minimum, the coordinates of the local minimum are 1, -2. Here's a slightly more complicated example. Notice here the arrows are pointing up, so that means it continues up in both directions. We want to know where it's increasing and where it's decreasing. So where it's increasing, that's as we move from left to right, we want to know where y is getting bigger. So that happens here and here. So those correspond to these intervals from -4 to -2 and from 3 off to infinity. So it's increasing from -4 to -2, union 3 to infinity, like so. And it's decreasing everywhere else. So it's decreasing here and here. So those aren't really very smooth, so let's try a little harder. There we go. So it's decreasing from -infinity to -4, and it's decreasing from -2 to, from -2 to +3. So -infinity to -4, union -2 to +3. Again, we don't include the endpoints of these intervals because at these local minima and this local maximum value, it's not increasing or decreasing. So let's just write down the coordinates now. So the local maximum, there's just one, which is this one right here, -2, 3. And local minima, there are actually two. So we'll use the plural. So there's one here, which appears to be -4 and -1. And this one appears to be 3, -2. -4, -1. And the other one is 3, -2, like so. Let me just fix my parenthesis here. Now, again, you have to be a little bit careful because the notation for intervals is similar to the point notation. So you have to be careful you know what you're talking about. Here we're talking about the intervals where it's increasing and the intervals where it's decreasing. Here we're looking at points. So these are points. These are coordinates of points that you see here. Now you also want to be careful about this because on the left here, from -infinity to -4, the function is decreasing. So don't be thrown off by the fact that the arrow is pointing up. That's just to give us some idea geometrically of what the shape looks like. The shape of this graph is continuing off in this direction as x goes to -infinity. However, when we're talking about increasing versus decreasing, we're asking what happens to the y values as x goes from left to right. So as x goes from left to right on this interval, the y values are decreasing. So we're starting out here at -infinity, or some really large negative number, and we're moving to the right. And as we move to the right, the y values decrease. So the function is decreasing on this interval from -infinity to -4. Let's look at another example. This one's a little bit more complicated. It has a lot of bumps and valleys, and each one of those bumps and valleys will give you a local maximum or a local minimum. So you can see there's a local maximum here, 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 and here. And there's a local minimum here, 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 and here. So that means that there's a lot of places where this is increasing, changing from increasing to decreasing. So it's increasing here, and here, and here, and here, and also here. So let's just write all that down. Let's change the color to green. So we'll say increasing. So it's -infinity to -3, union -2 to -1, and I'm running out of room already, union 0 to 1, union 2 to 3, union 4 to infinity. Let me just fix my pen seems to be dying on me here, so let's just do it like that. So that's increasing, and let's change the color for decreasing. So decreasing is decreasing here, 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 and here. So let's write all that out. So it's decreasing on the interval from -3 to -2. Shouldn't call it -3, it's -2, -3 to -2. Union -1 to 0. Union 1 to 2. Union 3 to 4. And now we can write down all of the local maxima and local minima. So local maxima, there are a bunch of them as you can see. So we've got one -3. They all have the same value though. They're all 1. They all have the same output value. So 3, 1, -1, 1. So -3, 1. And then there's 1, 1, and 3, 1. Now what about the local minima? local minima. So there's one at -2, and all of these have the same value too. These are all -1. These are all -1. And then, so there's going to be one at 0, -1, and 2, -1, and 4, -1. And those are our examples of local maxima and minima for this graph, or those are our local maxima and minima for this graph. Let's talk a little bit about the terminology. So if you have a local extremum, for example, at -3, 4, like you do in this graph, so at -3, 4, we say that the local extreme value is 4. So the output value of our function is 4. So that's our local extreme value. It occurs at the x value. So it occurs at x equals -3. So the local maximum value here is 4, and it happens at x equals -3. We also have a local minimum right here at 1, -2. So in this case, the local minimum value is -2, and it happens at x equals 1. So far we've been talking about local extrema. There's also a notion of absolute extrema. So if f at c is the largest value that f at x takes on over the entire domain, then we call f at c the absolute maximum of f. Using symbols, we say that f at c is greater than or equal to f at x for all x in the domain. So DOMF, here we're using this notation to mean domain. So in this picture, you can see that this point right here, the point has coordinates -1 and, well, who knows what that is. It's something between 4 and 5. But whatever this number is, that's the absolute maximum, because you can see that it's larger than any other output value. It's the highest place on the graph. So that's our absolute maximum. And it happens at x equals -1 in this picture. This one doesn't have a absolute minimum because this function just decreases without bound. I mentioned absolute minimum. What is an absolute minimum? That's the smallest place. So that's the lowest place on the graph. It's the smallest value. So if f at c is the smallest value that f at x takes on over the entire domain, then it's the absolute minimum. So f at c is less than or equal to f at x for all x in the domain. So this is a very similar picture to the last one. And you can see that the absolute minimum is right here. It's some value between -1 and -2. So this is the lowest point on the graph. And the lowest point on the graph is the absolute minimum. So this function has an absolute minimum but not an absolute maximum because it increases without bound on either side. It is possible to have both an absolute maximum and an absolute minimum. In such a case, you call the function bounded. So here are examples of two bounded functions. This one has an absolute maximum here at this point and an absolute minimum at this point. The graph on the right has an absolute maximum at x equals 0, and it has two places where there's an absolute minimum. There might be two places where there's an absolute minimum, but it's the same value. There can only be one absolute minimum. These functions are bounded because they have both an absolute maximum and an absolute minimum. This is the graph on the left, except magnified over so it's really over a smaller domain, or at least a smaller subset of the domain. So a function can have at most one absolute minimum. Here we have an absolute minimum at this point and at this point, but it's the same value. Whatever this value is, it's the same for both of them. So you can have only one absolute minimum. You can have at most one absolute minimum, but it might happen at multiple places. Here's a function that has an absolute maximum value of 1 and an absolute minimum value of -1. So you can see all of these values, all of these y values are the same. The maximum values are all 1, and the minimum values are -1. So the absolute maximum value is 1, and the absolute minimum value is -1, but each of those happen at many, many places. And in fact, this graph continues oscillating like this indefinitely. So there are infinitely many places that achieve the absolute maximum of 1, and there are infinitely many places where you can find the minimum value of -1, but there's only one maximum value, which is 1, and there's only one minimum value, which is -1. It just happens that they just happen at a lot of different places. Of course, there are some functions that don't have any extreme values at all. This function, it continues on increasing, and as you go to the left, it falls away like that. So this function is unbounded above and below. It just grows without bound as x goes to the right, and it falls without bound as x goes to the left. And so there is no absolute maximum or absolute minimum value. There isn't even a local minimum or local maximum value. One of the main goals of calculus is to figure out if functions have extreme values, absolute or local, and to identify what they are and where they are.